We'll start here very shortly. If anyone on Zoom can give me a thumbs up that they can hear me clearly, that would be very amazing. Thank you, Luke and Marco. Thank you, guys. We'll start here very shortly.
I swear to God, sometimes I just fail very obviously. And I swear to God, I'm trying. I'm just in the trenches. I think it looks like I just. Made the most.
Okay, let's go ahead and share this.
Scared. Oh.
Okay, it's at the 4:30 mark. We can go ahead and start. Good afternoon to everyone that's here and to everyone on Zoom. So we'll speak a few course logistics, and as usual, we have our slides. So here's where we are so far in the modules. So currently we're in week 3. Obviously, we didn't have a lecture this Monday due to Labor Day, so I'm hoping that everyone got a good break. For today, we're going to start with the application layer. And chapter 1 was basically a coverage and an introduction of what networking is. We spoke about structure. We spoke about topologies of network. We talked about the physical links, a little bit about the security, privacy, some of the malicious intents and acts that could happen. Today, we were going to speak about the application layer, which is the first layer in the OCI model. I'll give a brief recap for the ones that need it as a refreshment. So I also released Lab 1, which is the Wireshark assignment. And if we have some time today after our lecture, we will speak about it. But it's going to be pretty straightforward. I have released also a Wireshark setup and basics. This assignment was supposed to release on Monday, but I have released it early. For the ones that are familiar with Wireshark, they can get a head start. But it's not due now. It's due on September 21st. So you have a very good time frame to get used to Wireshark and whatnot with the Wireshark setup and the basics that's there. So let's go ahead and begin with our second chapter. And then if we have some time after, we will talk about the assignment in detail. Okay. So stop here. We go here. Present this. Okay, on Zoom. Let me just share my screen. Okay, perfect. Everyone can see the slides, right? Okay. Okay, so our lecture today will be about the application layer, and this is like from a top-down approach. As we discussed in networking, the application layer comes on first. So going from a top-down to approach, the application layer comes first, and it's really where it all begins when we speak about the networking and the infrastructure of networks. We all, as users, deal with the application, but there is a network infrastructure that goes in the background that we must understand. So today we're going to speak mainly about applications. Guys, if you could please just lower it a little bit over there. So today we're going to speak about the application layer in terms of the applications that are getting used by our users, and we'll give examples. We will also talk about the application layer in terms of the protocols that it provides for us. So it's the reason for the existence of the network in the first place. And it's going to support the network in terms of the applications that we really give it. So we'll start with applications that we're mostly familiar with and that we use in our everyday use. And we'll look at the protocols like HTTP, file transfer protocol, and very human readable and natural for us to understand. So that the application layer is a very great place to start. So this is just a slide that I have to read out. The session is being recorded, and an ample portion of the slide is derived from the book. And there's a very interesting activity that I will I suggest that you guys all look into regarding this specific chapter. Well, what we're going to speak about today. So here's the lecture objectives. We want to understand the role of the application layer when it comes to networking. We spoke about each layer in the first chapter, but very briefly. But once we go in detail to every layer, there's more to it than and there's a lot of details. Like for the application layer, we'll talk about HTTP, and there's a lot of details about HTTP. We're going to learn the principles of network application and their architecture, like client server, P2P, and hybrid. We'll explore how process communicates using sockets and addressing, using the IP port, IP address, and the port number. We'll also examine application layer protocols. We'll get to some of those today, but not all of them. But this is part of the application layer that we do cover. Also, we're going to compare the TCP and UDP. We said that TCP is more reliable. It acknowledges the data that it gets sent and received. UDP is more of a push. So maybe it could be used for streaming, such that the data is not very crucial, but that the video gets to the clients. We'll also talk about fundamentals of HTTP, like the request and response. There's persistent and non-persistent connection that we will dive into when we speak about HTTP. So this slide is a recap from the last chapter, and this one is very important, such that when we speak about today's lecture, everything is clarified. So this is how the data moves through the layers that we have. So data starts at the application layer, as we see, with a message M, also known as the data or the raw data or the payload. At the transport layer, a header HT, right here, as we see, is added, forming a segment. At the network layer, it becomes a datagram. And this figure highlights a segment and a datagram, but typically when we use either or, it's only one. It's either a segment or a datagram, depending on if we use TCP or UDP. At the network layer, another header is added, creating a datagram. At the link layer, one more header is added, making it a frame. And then notice that the encapsulation process, like each layer wraps the data with its own header, just like the Russian dolls that we've spoken about in the last lecture in the diagram. So the data travels through the physical link, and the process gets repeated again. So each layer at the destination removes its own header and processes the remaining data until the message is delivered to the application, also known as the client. So the key idea is that encapsulation hides complexity, so that each layer only needs to know how to talk to the layer directly below it or above it. Okay, so this is just end-to-end of a source and a destination. Obviously, we have the source and the destination, and this is more of a peer-to-peer model, but this shows how encapsulation and decapsulation works as the data travels from the source to the destination. So yes, at the source, the message starts with the application layer. It gets to the header. It gets headers added at the transport, network, and link layers, as we know. The frame travels across the physical medium, moving through the networking devices. And here that we can see, we have switches and routers. And we know that switches is different from routers when it comes to what they do. So we know that switches work only at the link and physical layers. That's why it's receiving it's from the physical link and physical layer. Their job is to forward the data based on the MAC addresses, the frame. So they don't care really about the IP addresses or transport layer information. That's why we have the router, and it deals with the network layer, because we know when the data moves down to the network layer, they add a header as known as the IP address of the source and destination. So they forward the packets based on the IP, making decisions about the best path to reach the destination, also known as we use the routing algorithm. Once the frame reaches the destination machine, each layer removes its corresponding header until the message is delivered to the application. So the takeaway from this slide is that the switch is for local delivery. It uses the MAC address / the link layer. The router is more global delivery that we talked about when we talk about structure of networks, as it goes globally and it goes more to regional. So it uses the IP and the network layer. So with the application layer, here's the overview of the chapter. We will cover maybe 2 points of these very in depth, but we will move to these until we finish the whole chapter. But here's the overview basically of it. The part of the networking that this is the part of the networking that most people actually see and interact with. Unlike the other layers, like the transport, the network, the link layer, this is the layer where end user services like web browsing, email, video calls, file transfer happens. We'll look at also the principles of the network applications, how they're designed, and how they run over the internet and what makes them efficient or inefficient. When it comes to protocols, we have various uses for them, and each one provides us with, maybe you can think of pros and cons. So this chapter focuses less on the nuts and bolts of headers and more on the protocols and services that support the applications. So the key idea here is that the application layer defines how programs on different devices talk to each other using the network. So here's the main goals of this chapter and what we want to accomplish. And I hope that you all leave with, when we wrap up to this chapter, is that we want to understand the principles behind network applications, how they're designed and what requirements they have. We'll look at different type of applications, how they're designed and what requirements they have. When we talk about application today, the first part of the lecture today will be about the applications in terms of development, not from terms of protocols. We will talk about the protocols as well. We'll explore how process communicates across network using sockets. And we do have an assignment regarding socket programming. So we will cover sockets briefly, but there is a main lecture for it. We'll also discuss the protocols like TCP and UDP and how applications make use of them. We'll talk about how various applications we have, what are the use of them and what they want to deliver such that they use certain protocols. We'll dive into some application protocols, HTTP, SMTP, all those that we see, the internet phone book, the DNS. So by the end, you should be able to connect what we use every day, like browsing or emailing, back to the network concepts that we've been covering. Okay, so when we speak about network apps, basically applications, we have a bunch of these, and there is ones that you use that might be not on the screen that are preferable to you. So we have the web, HTTP and HTTPS, browsing websites, streaming media, online shopping, the most familiar type of the internet app. We also have email, SMTP, IMP, POP3, still one of the oldest and mostly wide used application for communication that we use in our daily. We have text messaging, SMS, real-time communication requires low delay, but it's usually low bandwidth. We have remote logins, SSH, Telnet, that's used by IT professionals. We also have peer-to-peer file sharing, something like BitTorrent. We have the file transfer protocol, the FTP. It's a little bit older, but still relevant in terms of a method that moves the data files. And we have streaming media apps that YouTube, Netflix, Spotify, that are very known. We also have real-time voice/video, also known as VoIP over the internet that works. Skype is an example of that. And that we noticed that how each of these applications have a different requirement in terms of the bandwidth, reliability, and latency. Is there any applications that you guys use in your daily use that you can think of that could relate to this? Netflix. Although Netflix, it sucks that they added the advertisement to Netflix.
That's why you gotta get the TV subscription.
Really?
Yeah.
I
TV
see.
subscription don't have it.
Yeah, it used to be one subscription, right?
Yeah.
For everyone?
Mhm.
Oh, I see. And now they have added it to the
They gotta make more money.
stream east. They do. And the ads, it seems like to me, the ads at night, they become longer
Yep.
than the
Mhm.
daytime. It's because they know that we're
Yeah,
mostly
they
watching.
Get calm before not.
Yes. Okay. Although some ads that do come are very interesting. Did you want to say something? No? Okay. Oh, I see. Okay, cool. So for the architectures of applications, we have the known architectures here, client to server. We'll cover each of these in detail here. So there are main two models that we know. It's client server and peer-to-peer. And then they became a hybrid option that uses both of them. So with a client server, it provides services or resources. So when we speak about clients, those are the laptops, it could be phones, books, browser. It's connect to request information. An example of that is like the web browsing or sending emails. The advantage of using client to server, it's centralized management such that it's easy to maintain. The limitation of it is scalability. The server can become overload with too many clients. And that's what we see. For example, I was reading the book earlier for this specific chapter, and I think Google has 19 data servers, and such that they need more servers, such that there won't be an overload. The peer-to-peer,
I wonder how much Mark's person do
uh,
for his thing.
yeah, it's
Man, that thing is
massive.
massive.
Yes, and they expanded to like a lot of even after, yeah, a lot.
Produces. So you keep it real cool.
Exactly.
Moment.
So we have also the peer-to-peer. There's no central server. Each device is a peer, and they can act both as the client and the server, depending on what the use is. The examples is like BitTorrent. Some of you use BitTorrent, right? Or have you heard of it? Yeah, I used to. Okay. Advantages is very scalable. As more peers join, capacity grows. When capacity grows, it can become a little bit hard, but it's harder to manage and ensure reliability and security because each device is responsible for their own security. So that can become a problem. And then we have hybrid approach. It was also exists where application combines both models. I know that Skype is originally P2P, but they do have servers for directory lookups. So the key takeaway here is that client server is centralized control, P2P is distributed sharing. So here's an example of peer-to-peer, right? So we have various devices, and to note here, we have different operating systems, and every device has authority of themselves. Sharing could be made based on agreement, so that if the Ubuntu wants to access the network, there's a co-shared agreement with the other users that are in the peer-to-peer model. So it could become a problem when it comes to security because that there is no Active Directory or there is no centralized server that is built with the essential security to protect. Now, if we talk about client server model, here's the difference. We have a server here in the middle. Basically, you can think of it as the hub, and it has an Active Directory. It knows it can keep track of each user credentials, each user data, such that when Windows wants to access the network printer, it has access. So this becomes more efficient, but it's depending on the infrastructure that we want to use it. Sometimes peer-to-peer is efficient for us. Client server can be seen in bigger enterprises, bigger companies. So this is the part when we speak about applications, we're really not talking mainly yet about the application layer. We're talking about programs that get written by programmers that run on different end systems like laptops, phones, and servers. So the idea still exists that we have an application that connects with an application, whether the model is peer-to-peer or client to server. So we want to make sure when developers usually make applications, they want to make sure that it runs on different browsers. I mean, it runs on different operating systems. And examples of a network app could be a browser on your laptop, a web server hosting a website, a chat app on your phone. These applications rely on the lower layers, like the transport network, link, and physical. But we as programmers don't touch these layers. They're handled by the operating system and the network stack. So when it comes to development, we care about the UI, the back end, front end. Really, the infrastructure of networking is just there to help us deliver our data to the from a user to a servant image. So important, no need to write software for routers or switches. Routers or switches are built to forward packets, not run the applications. They operate at the lower layers, link and network. That's why when we think about networking, we can think of it as a dumb core smart edge. The intelligence is in the applications that we see in our daily use. That program is right, but not inside the routers. So if you want to build the next great app, could be anything like Zoom, Spotify, you really need to only need to program the end host, not the networking infrastructure. Okay, in a client server model, we need to clearly define the roles of a server and a client. Server is always on. It's always on and accessible over the network. It provides services to the clients. And those could be like email file storage, it could be anything. It's often located in data centers, and there are powerful machines designed to handle many requests at once. Could be Gmail servers, Netflix servers, and so forth. The client is the device that requests and consumes those services provided by the servers. Could be laptops, could be iPhones, could be anything that you can think of. Clients typically connect intermittently, so meaning that you open a browser and send an email or stream a video when needed. You're not doing that all the time. An example of that is your phone is streaming YouTube, your laptop is connecting to Canvas, and your email is the app. So the key difference is the server provides, the client consumes. So in most modern applications, we interact with the servers even without thinking about it. It's all happening in the background. Everything is very quick. With the peer-to-peer, it's the total opposite. Devices connect to each other directly without using the server. Every device acts as a peer by itself, and they share resources directly upon agreement, such as uploading, downloading a file. It's self-scalable, so as more peers join, they not only add demand, but also add capacity. So some of the challenges with peer-to-peer, as we discussed, they're not always reliable. Security is harder to enforce in comparison to client server, and finding resources efficiency can be complex. So as a takeaway, peer-to-peer is scales well, but sacrifices some control and reliability. Now, with applications, there's something called a process. So with an application that we built, it can have various processes, an application that can deliver at a time. So a process is just a program that is running on the host. Example to give you guys, when you open Chrome on your laptop and go to google.com, Chrome is the client process. On Google side, the server process is running on a Google server that responds to your request. Then the client process sends a request message, give me access to this homepage, and the server responds, that sends a response message back with the web page that you are requesting. In networking, applications involve process on different hosting communication systems. So we also have the IPC, which is inter-process communication. On the same machine, process may use system calls or shared memory. And across a network, IPC is achieved by sending messages over sockets. So basically, we have the applications, and we have application can have many processes, and those processes are delivered using the interface of sockets that we will talk about. So we often refer the process by their roles. Client initiates the communication, server waits to be contacted and provides the service. So networking at the application layer, process on different machines, talking to other via messages, which is the process. So we can have an application that process maybe 3, 4 things, 5 things at a time. It's all depending on the application that it's built. Now, to speak about sockets and to give you a visual of it, we know that we have the application that is being created, and application can have a process. I mean, we said that it can have many processes. The sockets is the interface that delivers the process to the other side. So to let the processes on different hosts talk to each other, we need a socket. And you can think of a socket as the doorway between the application process and the network. So when a process wants to send or receive data, it goes through the sockets. Think of it as like the API that connects application to the transport layer, like your TCP or UDP. there's two parts to keep in mind when it comes to sockets. Application developer controls what data to send, when to send, and to which socket. And operating system controls how the data gets over the internet, over the network, like using TCP or UDP, depending on the use of, or I mean, depending on the overall goal of the application. So without sockets, application won't have a way to plug into the network that gets transported to the network layer. So your browser, the client creates a socket to request google.com, the Google server, the server process, it has its own socket to listen for incoming requests. Two sockets connect, allowing messages to flow back and forth. So this is the idea usually of sockets. There is more in depth to it that we will cover on a different lecture. So to communicate, we must have a process, we must have a protocol. A process needs to be an identifier so the network knows where to deliver. So the identifier must be unique for each process to process communication. On the internet, the identifier consists of an IP address that we have. Usually the IP address of the server is static, it does not change, but the client IP addresses could change depending on which user requesting which request. The port numbers identifies the specific process on the host. And if we have an application that has many processes, we need to know which process is being responsible to do what thing. So that's why we use port numbers. They identify a specific process on the host. So together, the IP address and the port number uniquely identifies a process for us. And why not just use the IP, as I mentioned? Because one host can run many processes at the same time, and the port number tells the operating system which process the message belongs to, such that it can, when it gets requested, it gets sent back. Now, when we're talking about the application layer in terms of protocol and on the terms of application development or programming, this is where we dive into the application layer of the OSI model. So it defines how process communicates with each other over the network. Each protocol has a specific use. So there could be types of message that gets exchanged, like request, response, query, and reply. We will get to those in depth when we speak about HTTP. The message semantics, like what each field and what each message means. We have rules, how and when process send and respond. There's a means of rules that when the request and the response gets sent. So two categories of protocols that we mainly have. We have open protocols, and those are publicly defined, available to anyone to use. And those are called, I believe, as the RFCs. It's a rule book for these rules. And it can be implemented on various systems and various vendors. Examples of those could be HTTP, SMTP. And we have proprietary protocols. They're owned by a company and they're not always documented. So if a company wants to build their own protocol, they can. So protocols, their rules of communication, they make sure the applications understand each other. So when it comes to the application, they rely on the transport layer to provide certain services. There are key requirements the applications might have. One thing that they could have is data integrity, ensures the data is received exactly as the same way it was sent. Some apps can tolerate small errors like video streaming, others cannot, like file transfers. So it really depends on the application that is getting built and what they want out of it. If you're building a file transfer application where you care about the data, how it gets sent, make sure it's secured, it comes in, sends and receives in one piece. Some could be timing. They're looking for some apps need data delivered with low delay in real life. Like it could be video conferencing, games, or voice, VoIP, that's voice over IP. So, and also some applications need throughput, which we talked about. So they differ in how much bandwidth that they need, such that we have HD video streaming that requires more throughput than sending an email. Also security, some apps, then this is coming directly from chapter 8. Some apps need encryption, authentication, or confidentiality. So we have different applications demand different levels of these services, and that's why we have both TCP and UDP. If you're building an application for streaming, we just use UDP right away, such that we do want to deliver the stream or the video to our clients. We're not really worried about the security. But there is maybe a con with the time, such that we want, if there's a delay, it could be a delay of milliseconds or maybe seconds. It all goes back to the application that we develop. So here's an idea of different applications that we have, and what can they lose on, and where is their goal, and is time sensitive to them or not. So file transfer, like email, web documents, they require 100% integrity. No data loss is acceptable. Throughput is important, but not crucial. Like, for example, for an email, we want to make sure the content of the email gets sent. We really don't worry about the time as much. We know that it's going to get delivered, so it's not crucial. We have real-time audio and video. They can tolerate some data loss. Sometimes videos, they have it gets buffer, or there's a delay. That means, and maybe a dropped audio packet has happened, is okay, but throughput is a variable for higher quality, higher demand. So timing is very important. Delays or jitter can cause noticeable and disruption. Interactive applications like games, for example. And I'm assuming a lot of you guys game, right? Which game do you play? Call of Duty Zombies? Okay. The original ones are way better, right?
Indeed, have you played beta yet? The beta, the Battlefield, yes. Okay, all right, really good, that's just gonna make sure. My favorite, so Black Ops 1.
Yeah, that's an original.
Yeah.
So for games, data loss tolerance depends on the app. Some losses are often acceptable, but if we are playing a game and we are, as the player, we want to make sure our action happens before the other user, such that, and sometimes it happens, you're playing Call of Duty, and then you are moving and you have a chance of eliminating the other player, but it lags out and then you're eliminated. Yes, exactly. So it's very sensitive to delay. So responsive is more of a key for gaming. So not all applications need the same level of service. That's why we don't always use TCP. Sometimes UDP is a better fit for us. Here we have a couple of differences between TCP and UDP. TCP is a communication standard that lets the application programs and compute devices to exchange messages over a network. The way it's designed to send packets over the internet and ensures successful delivery of the data and messages over the networks. UDP is a communication protocol used across the internet for especially time-sensitive transmissions, such as video, DNS lookups. It speeds up communication by not formally establishing a connection before the data is transferred. So that's the difference. There is no one better than the other. It goes back to the application. Okay. Here we have various applications and various protocols and which transport protocol that they use. So SMTP, like the Simple Mail Transfer Protocol, the session is so we have various ones of the applications. We have SMTP, we have web documents, and this is what they use. So for like the protocol they use for email is SMTP, and RFC is like the detailed name that is coming from the blueprint. So there's various ones, and there's various ones that they use. So for email, we need TCP such that we can authenticate that the data that gets sent over the email is not lost, or it's not sniffed in a way that the attackers can read that data. For telephone, we can use TCP or UDP. For streaming video and audio, TCP. And it really goes back here, just examples that the applications, what protocols that they use. So we're gonna wrap up our discussion in terms of the application layer and the principles. We talked about what the application is from a developer point of view, the protocols that it provides, and that's ideally it. We have an application, and an application has various processes. Processes get sent using sockets, and we use the IP address and the port numbers. So now we'll speak about TCP a little bit. So by default, applications use vanilla TCP and UDP sockets, which provide communication but no encryption. That's why they came out with a TLS that we will speak about. So this means the data that is sent over the internet can be intercepted or read in a plain text. Anything that's shared with using TCP could be read. To secure that communication and to deal with it, they built TLS. It's not really a different protocol. You could say it's like an upgrade of TCP, because with TCP, we know that data gets sent and acknowledged. TLS is just a layer of security. So it provides encryption so the data can be read by attackers. Also provides authentication so that you know you're really talking to the intended server. Also provides integrity so the data isn't modified in transit. And usually TLS is implemented in the application layer, but it works on top of the TCP sockets. So most applications today, like web browsing, email, messaging, rely on TLS sockets. And we can see that when we go to some websites, if websites have HTTPS, that means they are using TLS. If they're using HTTP, that is the plain TCP, or also known as the vanilla TCP. So takeaway now, security is a must-have for modern applications, so that it's not just optional add-on, and a lot of applications use TLS with TCP. And I think some applications, like on the Google browser, they have a lock on the website. When you access a specific website, there's a lock that also means they're using TLS and it's secured. So now we covered so far part of, I would say, like a small portion of the application layer, the principles of network applications. Now we will move to the HTTP. We'll look at the real application layer protocols. We'll start with web and HTTP, one of the most wide used, I think, in our use. HTTP is a great first example because it's simple, easy to demonstrate, and something that every student uses daily. Oh, this one back, sorry. Okay. So when it comes to when we speak about HTTP and when we speak about web, a web page is not just a single file. It's a collection of objects. And objects are basically what's included in the website. So the most important object is the base HTML file that we have. You could think of it as the home web page. It defines like the structure on the page, and it contains references to other objects. So when you go to a page, you have the home page, about us, or contact us. Those are other objects. Pictures are also objects. Videos are also objects. So each of those reference objects is retrieved separately by the browser. A URL, we know it contains, in this example, two parts. We have the host name, which is www.someschool.edu, and this is the path name that leads to the GIF. So this is an object. So in this example that we have here, that we have this email here, it tells the browser which server to contact, and the path responds saying that the browser which file to fetch on that server, because we want to access this specific pic.gif. So when you request a single web page, your browser actually makes multiple requests. It does not make one request, because we are using various objects, and depending on the object that we want, there could be multiple requests. And this is where it comes the idea of persistent and non-persistent that we will cover when it comes to HTTP. So as a takeaway, a web page is the base HTML file. Multiple objects are all fetched via their URLs. So here's an overview of HTTP. And here we look at, I think there's supposed to be animations. Yes. There we go. So here we start looking at the web and how it actually works. We type a website or we click a link. The communication happens using a protocol called HTTP, which stands for Hypertext Transfer Protocol. So to explain it in plain terms, think of it as a you think of it as a universal book, that a rule book that both browsers and servers agree on. Without it, your browser wouldn't know how to properly ask for a page, and the server wouldn't know how to respond. So to the diagram here, on the right, we have a server that is running. That's a machine somewhere on the internet storing websites and data. On the left bottom here, we have an iPhone, and the top we have a PC. So the client is any device that initiates the conversation. When you type in www.ucf.com on your browser, the client sends a message to the server saying, hey, please give me this homepage. And then this is called an HTTP request. The server, what it does is it acknowledges the request, depending if we use TCP or UDP. The server then checks what you asked for, and it finds the right content, and it sends it back. So this could be maybe images, resources that you're requesting. So notice there's a two-way street between them. Requests always come from the client, and the response always goes from the server without back and forth. So websites won't load. So to wrap up of an overview of HTTP, the takeaway is that the web is a base, simple request response cycle. Clients ask, server responds, and the HTTP is the language that they use to communicate. Now, to continue on HTTP doesn't work alone. We know that it uses one of the data transfer protocols, and it could use TCP. So the reason that TCP is reliable, it makes sure that all little packets of data arrive safely and in the right order. Imagine downloading a web page, you won't need any missing images or jumbled text that you are downloading. So another key feature of HTTP is that it's stateless, which means that each request is separate and independent. So when you ask for a specific object, and then you request another object, it does not remember that you requested the first object. So for example, if you have ucf.edu opened on one tab, and then when you go request UCF again, not knowing, it does not really remember that, hey, you have asked for this before. The server just goes back to the traditional request and response. So address on the side box. Why keep HTTP stateless? Because remembering history or remembering state makes things complicated, such that if the server is keeping track of every user, it suddenly crashes, and the memory of those interactions might be lost or mismatched. So it is very difficult. So stateless design keeps HTTP simple and robust. But sometimes that we see, like when we close Google Chrome and when we open it, there's the option to restore the pages automatically. So to wrap up, there's two key takeaways here that we want to deliver, that HTTP rides on top of TCP to guarantee reliable delivery, and HTTP itself is stateless, which makes it simple, but also requires extra tools like cookies when you want persistence. So we will talk about HTTP more in detail in the next lecture as well. So here, when it comes to non-persistent and persistent, and those are the two types of connections when it comes to HTTP. So let's talk about non-persistent first. Every time the browser requests something like an image or a style sheet, it opens a new TCP connection. That means a web page with 10 objects, it will open 10 separate connections. This creates extra delay. On the other hand, we have HTTP persistent, also known as HTTP 1.1. It keeps the connection open. The browser can send multiple requests through and get multiple responses back. It reduces the overhead and makes loading much faster. So persistent HTTP is more efficient and what browsers use today, starting from HTTP/1.1. So you can think of non-persistent means one connection per object. Persistent, we keep the connection open for multiple objects. So here's an example that we will use to demonstrate this. Here's an example of persistent HTTP actions. Let's assume that in step here 1A that we have the client enters a URL like that we see here is someschool.edu and access for a web page that contains text as a reference of 10 images that we see here. So client initiate a request. The client user computer initiates a connection to the server. So step 1B, which is the server, a response to it, it says, hey, the server accepts the connection from the client. Now we are ready to communicate. Okay. Step 2, so the server sends an acknowledgement back to the user, which is in step 2. Step 2, client sends a message, says, hey, I'm asking for this specific web page. Please give me access to it. The server sends a response back that, hey, we got your request, and response with the base HTML file. So the base file includes not only the text content, but also references like the links of the 10 images. Because this is non-persistent, each of those images would require a separate and new connection and repeat of this process. So if we have 10 images, this gets repeated 10 times. And I have it in the next slide here. So after it requests the first object, the first image, the server closes the connection. And this happens because we're using non-persistent. And step 5, client receives the response. Now the browser parses through the HTML and sees that it contains references to multiple images, and then the process gets repeated for each of the images here. So open a connection, send a request, get a response, and close the connection again, one by one. There's also something that we need to, oh yeah.
So why does HTTP use TCP and not TLS?
So so that's what we spoke about. Some websites use HTTP without the S. That means without the TLS. Some why they use it because I can look into this more, why actually some websites don't use TLS, since as us as developers, when we build a website, we want to make sure that it's secured. So there must be factors that when it comes to development, maybe as TLS could be costly to include. I can look into that more in detail, but that's a very good question. Yes.
Actually, no, like the site, I just look at it says.
Yeah.
Or site.
Safe side, exactly. You have to get it, yeah. Go ahead.
So basically, HTTP is generally not with TLS.
Yeah,
HTTPS, the S is the with the TLS context.
Correct. yes. That's why, yeah, that's why some websites that we know they're very mainstream, they use usually TLS with them. But starting websites, sometimes like local businesses, they don't consider that because they just want their web page displayed for customers to access it, and that's it. So when it comes to HTTP, we have to keep an idea of time. And when we speak about networking, we spoke about throughput. There's delays with the packets and the router with the buffer. So time is a very important factor that we will speak about throughout the semester. So RTT stands for round time trip. Also here we have a comment, you guys cannot see it, but it says that HTTP is usually cheaper than HTTPS. So when you're handling your own server, you have more cost to maintain. Thank you, Carla, for your comments. So round time, RTT, round trip time is the time it takes for a small packet to travel from the client to the server and back again. You can think of the network latency for the round trip, this an idea. So per object, to fetch one object over HTTP with non-persistent connection. The response time includes one RTT that we see here to establish the TCP connection. And then we have another RTT for the client to send the HTTP request and receive the first byte of the response. So transmission time for the server to send the entire objects. And we said with non-persistent, the request gets repeated. So if we have 10 objects, we're gonna need 2 for each one. So you do the math, we're gonna need 2 for each objects. So let's keep that in mind. So on the figure here, we have the client initiates a TCP connection that costs 1 RTT. Next, the client requests the file and waits for the server response. That's another RTT. Finally, the file is transmitted across the connection, and the time is to transit is shown in is it shown here in blue? Yes. It's actually not shown in blue, but there is a time that's associated with it. And it's usually not that much. So for each object with non-persistent, total response time is about 2 RTTs plus the transmission time between the client and the server. There could be some issues that could arise with non-persistent and persistent. So for non-persistent, it requires, like we said, 2 RTTs, one for setting up TCP and one for the request and response. Sometimes the OS can overhead. Opening and closing too many TCPs connection consumes extra resources, both from the client and the server. So what tends to happen is that browsers can open parallel connections to compensate, rather than having that initial way. So browser often open multiple stimultaneous TCP such that connections will happen in parallel, which can overload the server if we do it the original way. So persistent HTTP, which is 1.1, when connection is for multiple objects. So it's more efficient. TCP stays open for several requests and responses can reuse the same connection. It's also less overhead. There's no need to repeat the communication setup every time. Pipeline possible such that clients can send multiple requests without waiting for other responses. Maybe it controls the congestion and traffic, and it's much faster so that RTTs overall, it makes web pages load more efficient. So the takeaway and comparison to wrap up about these is that non-persistent is always inefficient and repetitive because we said it gets repeated per object. And persistent is, you can think of it reusable, efficient, and is now the standard since HTTP 1.1. So here's just a detailed of a HTTP request message that we have. And this is what I was talking about, the interactive session. That's really cool. I was messing with it yesterday. It basically gives you a request message here, and it tells you to answer some questions based on the request message. So we need to be aware of a few things when we look at the request message. So a request message begins with the request line, and that's usually could be get, post. That means the request has been initiated. The request like get is the same as post, vice versa. So it also includes the URL that we're trying to access, index.html. It specifies the HTTP version, which is 1.1. We said that is persistent. Let me just refer back to it. I do not want to. Yes, persistent HTTP, which is 1.1. And the lines ends with /r/n, that such we know that the request has been closed and has been opened in the top over here. And it also comes with header lines, as you see there, that we can see like the host that's being contacted, the type of browser making the request. I think here they're using Firefox, which I don't like. I like more of Chrome, but yeah. And the type of object that the client can accept is also shown here, such that accept text HTML. as shown there. The preferred language is also something EN/US. I think that's standardized for English language, and whether the connection should stay alive or not. And this is the idea of persistent. When we talk about persistent, the connection is alive. Non-persistent, it is not alive. So the message ends with a blank line. This marks the end of the headers. And you can see the structure is like very simple and human readable. Yes.
This. Like the
Mm.
non-persistent.
Yes.
So the non-persistent.
Mhm.
Every single individual request for some object that's made, so every object. You can see over every single object.
Yes. So the handshake that we spoke about here gets repeated for every object. Exactly. Yes.
Persistent, the connection opens and it keep requesting, but that will not.
Yes.
So how does the persistent know when to kill the connection?
The person it's based on the client.
The client will send the message saying, hey, I'm done.
No, I mean, usually like if you're going on a website and you download a file and you download maybe 3-4 files, when you close out your browser, that initializes that, hey, the request is being done. And when we look at it here from the detailed of HTTP request, the //rn is like the end of it. That's if we look at a deeper level.
The bottom there. Well, is that like a system where we can send information back and forth, like, hey, I'm still there, hey, I'm still there.
Exactly, yeah.
Yeah.
If we look at another example, that will change for non-persistent, but persistent is keep live. And this interactive session is really nice. The slides have been uploaded if you guys want to go and mess with it. So this is it. So the conclusion is the application layer enables end-to-end communication between processes. We said that we have applications. They go to processes. Processes get interfaced by using sockets. Network applications follow client server or peer-to-peer models, and we spoke about the different use of them. Sockets provide the interface to communicate across the host. So the server has a socket and the client has a socket, and that's one of the cool assignments that we will do in here. Protocols define the message types, syntax, semantics, and rules. We talked about open versus disclose, and maybe some companies want their protocols to be disclosed. If they were open, there's a rule book that defines those specific rules. Transport needs differ by applications. We said that some applications need reliability or timing, throughput, or security. So HTTP is a key web protocol. It uses TCP, stateless design, meaning that it does not remember that you requested something within a page. Every request that you make is individual. Non-persistent requires multiple connection. Persistent, which is HTTP 1.1, improves the efficiency. So that's the idea so far of that we will talk about HTTP. We said there, we looked at our request. Next lecture, we will look at the response, and then we will continue with the chapter till we finish it. And then we will move down to the next layer after the application. So now I think we have some time to speak about the assignment that I released today. So let's look at here. Let me share my screen because I think it did not share. Okay. We are in week 3. I want to open these 2 specific things. First thing first that I wanted to speak about is we uploaded this as you can think of it like a guideline, an installation guide about Wireshark, and it gives a brief introduction. So let's zoom in here. So yeah, it talks about how to install Wireshark, detailed, and visualizes it step by step, those that are not familiar with it. And we also want to enable NCAP here. This is to capture live network traffic. So it gives you the option. Make sure you do click that because that is very important. And I was not planning to release this assignment today, to be frank with you. I was wanted to release it on Monday because of the Wireshark. But since most of you are familiar and I gave it more time, so that's that should be fine that for the students that want to work ahead. For the Mac, here's the guidelines for it. It's the same thing, so you can refer to this with that, and it has some basic things that you can see here with the design of it. So you can always refer to that. For the assignment, it's going to be we have 2 questions, but there's various parts to it. So that we have some guidelines here, how to set up Wireshark and a video, some manual pages. I also uploaded the PDF that you should guys refer to. And it's going to be basically very simple and close to what we discussed here. So you will open these following URLs, you will answer them. When you answer these questions, please put images. Even if you cannot get a detailed answer, show what you have achieved and show what you can do because it will be compensated. Yes.
No question other than showing the picture she wants to write, like sentence or two.
Just like steps. So like, oh, I first I clicked this, I got that, and then just put up an image. And sometimes, usually I recommend to the students if the image contains a lot of information and you want me to see something specific, or the TAs highlight that, make like a text box or with a red indicator such that it can be there visually. So that is it. Usually here's some hints. If you have any questions about the grading will be very detailed. So when you receive your grade, there will be comments. You can reach out to the TA for help. You can reach out to me, and I think this is a good assignment to start with. So that is it for today. Class is dismissed. If you have any questions, come and ask them. After that, we will cover the next part of the application layer. Thank you to everyone on Zoom. Yes, sir.